Assalamualaikum and a very good afternoon. So today we are going to continue with Fourier transform application. Okay, the last part of chapter 3 is Fourier transform application. So let's look at this image. The input image originally very sharp, and when you look at the magnetic spectrum, you cannot actually see the main shape of the original signal. So therefore, by using a filter, you can get the output spectrum as similar as the input signal. So this is where the Fourier transform takes place. We are going to look at the Fourier transform application in terms of three main applications. The first one is the modulation process, and also filter application. Okay, before that, let's have a quick recap on the symbol or operation that you may find in a system. So for example, the mixer or a multiplier, multiplexer, that's basically adding or perform a summation of multiple signals. And then a filter, when you have an input being convolved with internal signal, and then gain when the amplitude of the input signal being scaled up or being amplified, and lastly when it involves multiple operations. Okay, so what is a filter? A filter basically selecting required signals and attenuate or remove unwanted signals. Okay, there are three common types of filters, which are the high pass filter, low pass filter, band pass filter, and also band stop filter. Okay, the first type of filter is the high pass filter, in which it will pass through the higher frequency components and attenuates or remove the unwanted lower frequency components. And the border between the lower frequency and the higher frequency component is defined by cut frequency, omega c. Omega c is basically takes place when the power is reduced by half. Okay, so for example, the maximum power is 1 watt. So the cutoff frequency is basically when the power is 50% of the maximum power. Okay, so this is where the cutoff frequency, radian per second or hertz, takes place. Okay, so the higher frequency, the high pass filter frequency response looks like this, in which higher frequency component will be selected or will be passed in, and lower frequency component will be removed from the system. Okay, and this is how the transfer function of the high pass filter looks like, in which you can see it's basically the combination of rectangular signal. Okay, if you recall back the rectangular function, for example, you have this is A, and when you remove the middle part, so when you remove this area from negative omega c to omega c, so it's basically A minus the middle rectangular, so the amplitude is A rectangular, this is omega, so omega over 2 omega c. So this equation can be simplified into this. So this is the transfer function of high pass filter. Okay, this slide summarizes the basic information about cutoff frequency. Is that it is also known as corner frequency or break frequency, in which it is a boundary in a system frequency response at which energy flow through the system begins to be reduced or attenuate rather than pass through. Okay, the 3 dB point is also known as half power, as mentioned earlier. It's happening when the power is reduced by 50% from the maximum power. Okay, you can have a quick glance on the example how the 3 dB points or the cutoff frequency is calculated. Okay, let's look at the example on application of high pass filter. Okay, given two signals that being multiplied together, so you have two input signal G1 and G2. So in this case, for example, G1T being multiplied with G2T, and the output is G3T. Okay, so when you multiply both signal in time domain, so you have 2 multiply with 5 is 10 cos 200 pi and cos 100,000 pi. So when you use trigonometric identities, you get 5 cos 1200 pi t plus 5 cos 800 pi t as G3. So this is the output signal in time domain. So by using frequency domain or by referring to Fourier transform table, so you can expand this equation into frequency domain. So if you have cosine function, so the equation will be pi del omega minus omega naught plus del omega plus omega naught. So omega naught is basically the frequency of the signal. So now G3 in time domain being transformed into frequency domain by using Fourier transform. So you have both component in positive and negative frequency for different frequencies. In this case, you have 1200 pi and 800 pi frequencies. So in terms of spectrum, okay, so you notice that you have the negative 1200 and positive 1200. So you have negative 1200 and positive 1200, and the amplitude is 5 pi. And the next one you have 800 and negative 800, and the amplitude is 5 pi as well. So this is the spectrum of the output signal. Okay, assuming that the system require a specific output. For example, the system require an output given by G4 equal to 3 cos 1200 pi t. So if you convert this into frequency domain by using Fourier transform table, so you get this component. Okay, however, if you flip back to earlier slide, the output of the system is currently G3. Okay, meaning that you have the input G1T multiply with G2T, it produces G33. However, the end recipient only require G4, meaning that you need to do something, you need to perform some filtering here to make sure that any unwanted signal at G3 can be removed and only G4 will be received at the end. Okay, if you compare G4 and G3, so G4 only require component at 1200 pi and positive 300 pi, meaning that the system doesn't require the lower frequency component. So in this case, you need to use the high pass filter in order to pass in or to select higher frequency component. In this case, the frequency is 1200 pi, both positive and negative frequencies, and remove the lower frequency component. So in order to do this, so this is the complete spectrum G3, and you need to apply a filter. Okay, a filter so that only higher frequency component will be selected and the lower frequency component will be removed. And please take note as well the amplitude of the output. Okay, at the output point, the amplitude required is only 3 pi, but G3 you have the amplitude 5 pi, so that you need to design the filter that select higher frequency component and the amplitude being compressed to only 3 pi, meaning that the output should look something like this. So once you have this, meaning that your filter may look like this. Okay, the filter usually giving the notation as H omega. Okay, and this is negative omega c, and here is omega c. So the frequency required only at negative 1200 pi and positive 1200 pi. Okay, so the magnitude of the filter. Okay, so what's the magnitude of the filter? The magnitude of the filter, or the magnitude of filter is defined by the ratio between the amplitude of output, or the required output, divided by the amplitude of input. So in this particular case, the output required is 3 pi. So it is basically 3 pi divided by the input is 5 pi. So this is basically the magnitude or the coefficient of the filter. Okay, so now, as mentioned earlier, so this is the filter response, the high pass filter response. So the magnitude is, in this case, 3 pi over 5 pi. It's basically the ratio between the output amplitude divided by the input amplitude. And the transfer function, or the equation of the filter, can be written as H omega equal to, so the magnitude 3 pi over 5 pi 1 minus rectangular omega divided by 2 omega c. So what is omega c? Omega c can be any values as long as it is lower enough than 12,000 pi, 1200 pi. However, it must be larger enough than 800. Okay, so omega c lies in between here. So it must be larger than 800 but lower than 1200 to make sure that no signals from 800 pi will be included in the filter, and to make sure the component at 1200 pi completely being selected and passed through the filter. Okay, so this is the transfer function of the high pass filter for this particular case. On the other hand, the filter response can also be written as H omega equal to the ratio of the output over the input signal. Okay, now let's look at the low pass filter. So low pass filter will select in or will pass through low frequency components and attenuates higher frequency components. Okay, so the lower frequency component that will be selected is basically included within the passband area, and the unwanted signal that will be removed from the filter lies within the stop band area. Okay, so this is how the frequency response of low pass filter looks like. So here is 3 dB. Remember, minus 3 dB from the maximum power. So this is where your omega C takes place. So the frequency response of the low pass filter can be illustrated as this. So this is where this lower frequency component will be passed in or passed through, and the higher frequency component will be removed from the system. So the transfer function or the equation of the low pass filter is expressed as A rectangular omega over 2 omega C. Okay, let's look at an example for a low pass filter application. So let's use the same example as the earlier one in high pass filter. So again, you have the input G1T multiply with G2T, and you have the output G3T. But in this case, the system requires the output as G5. So meaning that you need to apply a filter somewhere here so that the output GT, the earlier output GT, is processed so that only G5 is received at the receiving end. Okay, so in this case, from earlier example, so G3 in frequency domain equal to this equation in which we have two different frequencies, 1200 pi and also 800 pi, both in positive and negative frequencies. However, the final output required is G5 when this one being converted into frequency domain. So it is basically 4 pi del omega minus 800 pi and plus 800 pi, meaning that only the component at negative 800 pi and positive 800 pi will be selected, and the higher frequency component, in this case 1200 pi, will be removed from the system. So in order to do this, you need to apply a filter. So the filter will only allow the lower frequency component inside the filter and remove the higher frequency component. So this is how the filter response looks like, in which the cutoff frequency must be larger than 800 pi but lower than 1200 pi. How about the magnitude of the filter? It's basically the ratio between the output over the input amplitude. So in this case, the output required is 4 pi over the input you have is 5 pi. So you get 0.8. Okay, so this is how the output signal looks like. Output signal in which you G5 in this case. Okay, so how about the equation of the filter? Okay, you can see the rectangular shape here. So your H omega in this case is equal to the magnitude 0.8 rectangular omega over 2 omega C. So don't forget to define the range of omega C. So omega C must always be larger than 800 pi but lower than 1200 pi. Okay, same goes to when you have a band pass filter. So but band pass filter allows certain frequency range and attenuates signal outside the range. So this is how the band pass filter looks like. Okay, in which the specific range of components will be selected, but the rest of the component will be removed from the system. And the transfer function of band pass filter can be expressed as the A. So this is the first one, the bigger rectangular minus the smaller rectangular. So in this case, the bigger rectangular is negative omega CH and omega CH. So it's A rectangular omega over 2 omega CH minus the middle rectangular. So minus negative omega CL and omega CL minus the A rectangular omega divided by 2 omega CL. So what is omega CH and omega CL? Omega CL is the lower frequency, the lower cutoff frequency of the filter, while the omega CH is the higher range of cutoff frequency of the bandpass filter. Okay, next application that will be discussed in this chapter is modulation process. So basically, this is one of the important techniques in communication system to transmit low frequency signal. Why we need modulation? Okay, because low frequency signal is easily affected by the noise. Therefore, the low frequency component need to be modulated by using a stronger carrier frequency, so that the input signal, the lower frequency signal, can be transmitted over the channel or over the transmission medium efficiently. Okay, so lower frequency component usually easily affected by noise. So for a complete communication system, for example, you have an input signal MT. This is the input, or also known as modulating signal. Okay, the input signal will be modulating the carrier signal. Okay, CT. Okay, meaning that the input signal will modulate the carrier signal in order to get the output signal, in this case XT. Okay, so the signal will be transmitted via a channel or transmission medium, so until it receives the receiving end. So this part, the first part, is the transmitter part, and the final part is the receiver part. Okay, in the receiver part, so now the XT is received, and the XT will again be multiplied by a carrier signal that's having the frequency more or less equal to the earlier carrier frequency signal. So again, with carrier signal having omega C frequency as in the first place. Okay, so now the signal having the final output, for example, YT. Okay, and there will be a filter here, usually a low pass filter, so only lower frequency component will be selected and the higher frequency component will be removed. Okay, so at the transmitting end, the modulation process takes place, while at the receiving end, a demodulation process takes place. Okay, the first part, the signal being modulated. Okay, so the output here is called modulated signal. The modulated signal being transmitted through a channel or a transmission medium, and then received at the receiving end. The signal again being multiplied with a carrier signal having omega C more or less equal to the earlier one. and then the signal being passed through a filter, a low pass filter, so that the low frequency component will be selected and the higher frequency component will be attenuated. Finally, you get the final output signal. Okay, let's look at an example on amplitude modulation application. So you have the input signal modulates the carrier having the omega c frequency, yields the output xt equal to mt cos omega ct. So if you convert this cos omega ct into exponential form, so you'll get the input signal now having both sides in the positive and negative frequencies, while the magnitude being cut into half. So same goes to when you refer to Fourier transform table or Fourier transform pairs. When you have ft cos omega ct, so you will see that the frequency domain will be having a split of frequency, one on the positive and one on the negative side, and the amplitude also cut into half. So in this case, in terms of the spectrum representation, so this is the input signal, mt produce m omega in frequency domain. So after multiplication with ct, so now x omega, the output signal, being divided into two parts, on the negative and positive sides, while the amplitude being cut into half. So this the equation of the output signal in frequency domain is this x omega. Okay, as discussed earlier, once the amplitude, the signal has been modulated at the transmitting end, so at the receiving end, the signal will be demodulated so that the input signal can be recovered back. Okay, so assuming that this is the receiving end, so here is the channel. Oops. Here is the channel or the transmission medium, and here you have the xt, the modulated signal. It's the multiplication of ct, the carrier, and also the input signal. So here is the modulation process, while at the receiving end you have the demodulation process. Okay, the signal, the modulated signal will be multiplied again with ct, having the cutoff frequency of omega c, and then the signal will be passed through a low pass filter so that the lower frequency component will be removed and the lower frequency component will be selected and the higher frequency component will be removed from the system. At the end, the original signal will be recovered back. Okay, in terms of mathematical representation, so at the receiving end, so this is at the receiving end in demodulation process. So the signal xt is multiplied with the carrier signal. So now you have, when you do the Fourier transform, so you will get two components in positive and negative frequencies, while the amplitude is cut into half. So here you have the x omega. So x omega is basically from xt, from the original signal, from the modulated signal given by this equation. If you refer back to modulation process, so this is basically the output from the modulation process. So now the modulated signal being demodulated by the carrier signal. So the equation can be further expanded, and then the output signal you get is this, in which we have 1 m omega. This is m omega minus 0 here, and then at negative omega c and positive omega c. So positive to omega c and negative to omega c as the center frequency. So after the demodulation, you have now three components. So you have the lower and upper frequency component, and you have one in the middle. Okay, this is for this one. Okay, so after that, the signal will be passed through a low pass filter. Okay, so now you have a low pass filter that will select the low frequency component only and remove the higher frequency component. Okay, so the magnitude of the filter is the ratio of the output required. So in this case, the original having amplitude of A, so the output must be having the amplitude as A as well, divided by the input. The input of the low pass filter, okay, the input of the low pass filter having the magnitude of A C divided by 2. Okay, AC divided by 2. So now when this one is supposed to be AC as well, or you can just simplify this one into A. Okay, so you get the magnitude of the filter is 2. In order to get the amplitude as the same or as similar as the input signal, so after you apply the low pass filter, you can recover back the original signal as similar as the input sent at by the transmitter. So you need to perform some mathematical derivation to see the relation between the modulated signal and also the signal after demodulation process. Okay, that's all basically on Fourier transform application. So next, I'll be discussing on more examples on Fourier transform properties and applications, and I'll include some of the past year's tests and final exam examples as well. Thank you.